In this lesson, we're going to talk about numerical integration. And basically, we've discussed this before way back when we were first learning about how to calculate the area under a curve. We discussed Riemann sums. We discussed finding rectangles that fit under the curve. We talked about the smaller the widths that we make those rectangles, the more accurate our area is going to be. Well, we're going to use some similar techniques in this lesson. And so the first one we're going to talk about is the midpoint rule. And so basically we're going to look at rectangles underneath the curve, just like we did before, but rather than use the left endpoint or the right endpoint to find the height of the rectangle, we're going to use the midpoint this time. So if this is my rectangle here, I have 1, 2, 3, 4 rectangles here. So the solid line shows us the boundary of the rectangle. The dashed line that comes up through the middle is where our midpoint is located. So we are going to find the area of those rectangles, but we're going to use the midpoint to determine the height of the rectangle. And so here is our midpoint rule. We're going to use the given function to evaluate our midpoints to find the height of the function. We're going to add those all up and multiply by the width, and that will give us the total area as an approximation. Now this notation here means we're using the midpoint formula, and we're going to use 4 intervals. So using the midpoint rule, we're going to estimate the area under the curve between 0 and 1 of x squared, and we're going to use 4 subintervals. We're going to compare the result with the actual value of this integral. Okay, so if I look at the interval from 0 to 1, and I split it up into 4 intervals, that means to find the width of my rectangles, I need to take the width of my interval and divide by 4, so it breaks it up into its 4 intervals. So in this case, I'm going to use rectangles that have a width of 1/4. So my endpoints, my right and left endpoints of the rectangles are going to be 0, 1/4, 2/4, 3/4, and 1. But we're going to use the midpoints rather than the left or right side of the rectangles to evaluate the height of that rectangle using the function. So to find the midpoint, a quick review, I take the left endpoint and the right endpoint, I add them up and divide by 2. That will give me the center. So for this one, I would take 1/4 plus 2/4 and divide by 2. So when I go through the process and find each of those midpoints, I'm going to find that the midpoints are 1/8, 3/8, 5/8, and 7/8. Now the width of each of those rectangles we already found was 1/4. So to find the heights of the rectangles, I'm going to take the value of the function at 1/8, 3/8, 5/8, and 7/8. When I add up all those heights and I multiply by 1/4, because those are the width of each of those rectangles, I'm going to get, let me move this out of the way, I'm going to get 0.3281. Now, you can certainly do this by hand. It's not hard, but it takes a little bit of time. There is a way you can do this on the calculator and let the calculator do the arithmetic for you. So, to find the area using the calculator and let the calculator do all of this arithmetic for you, what you're going to do is you're first going to go into your function, and you're going to put in your function, which in this case is x squared. Then what we're going to do is we're going to go and hit the button that says Stat and choose the Edit option, and we're going to edit our list. Now, if there's something already in there, you can clear it out by arrowing up and highlighting L1 and hit Clear, Enter, and that will clear out the list for you. All right, so what we're going to do is in our L1, we're going to enter our midpoints. We said our midpoints were 1/8. So I'm going to put in there 1 divided by 8, 3/8, 3 divided by 8, 5/8, 5 divided by 8, and then 7 divided by 8. So these are the midpoints, and these are the values that we're going to use to plug into the function to find the heights of the rectangle. So now remember that this is in list 1. It's important to remember what list you put it in. So we're going to go back to the home screen. Now I want the calculator to evaluate all of these midpoints all at once for the function x squared. So what I'm going to do is I'm going to hit the vars button here, over to y vars, choose function, and I'm going to choose, since I put my function x squared in y1, I'm going to choose y1. And just like using function notation, I'm going to tell it to do y1 of list 1. That was where we put all of our midpoint values. So you have to use parentheses, and then your list 1 button is right above the 1 button. It says L1 in blue, or mine's in blue at least. Yours might be in a different color. So I'm going to hit second 1, and the L1 will come up. I'm going to close the parentheses. And so when I do that, what's going to happen is the calculator is going to evaluate all of those values in list 1, all of my midpoints for the function in y1, which is our x squared. And I want to take that and I want to store it in L2 or some other list. So I'm going to hit the store button, and then I'm going to hit second 2 to tell it to choose list 2. So I'm telling it now to evaluate all of those midpoints, and then I'm telling it to put it in list 2. So I'm going to hit enter. And now when I go back to my list, if I go to stat and edit, all of my values are evaluated very quickly. All of my midpoints are evaluated very quickly. So now I know that these are all the values of my function in list 2. So if I go back to my home screen, I can tell the calculator to add all of those up again, because that's what we want to do. We want to add up all the heights and multiply it by the width of 1/4. Above the stat button in a different color for your shift, there's a list option. So we're going to hit second stat. I'm going to go over to math, and I'm going to tell it to use option number 5. I'm going to tell it to add up all of list 2, because that's where we put our values of the function. So I'm going to put in there L2, close my parentheses. Now it's going to give me all of these values added up. So my last step is just to multiply by 1/4. So times 0.25, and I get the same answer as I did if we did it by hand. Now that's a lot of steps, but once you get familiar with where everything is located in the calculator, I truly feel that this makes it a lot easier, and it's less likely for you to make a mistake this way. So I encourage you to use this method, but I'm not requiring it. Now, we can also apply this idea for finding the arc length of a curve. So I want to use 6 intervals. This is M6. So we're going to use the midpoint formula and 6 intervals. And we're going to estimate the length of the curve 1/2 x squared on the interval from 1 to 4. So if you recall, what we need to do to find the arc length is we need to find the square root of 1 plus the derivative of the function squared, and then we have to integrate it over the interval. So in this case, our function is 1/2 squared, so I'm going to take the derivative of this, which would just be x, and I square it, so that's going to go in here. So the function that we're going to use to find the length of the curve from 1 to 4 is the square root of 1 plus x squared. Now, to find our endpoints and our midpoints, since this is on the interval from 1 to 4, I'm going to find the length of the interval and divide by 6 since we're making 6 intervals. And I find that we get lengths of intervals of 1/2. So my endpoints for the rectangles are going to be at 1, 1.5, 2, 2.5, 3, 3.5, and 4. And then to find my midpoints, I have to add them up and divide by 2. So here are all my midpoints. And when I did that, I got a midpoint of 1.25, 1.75, 2.25, 2.75, 3.25, and 3.75. So to find the approximate length, I'm going to evaluate the function, this function here, at each of the midpoints. I'm going to add them up and then multiply by 1/2. I put a comma here, that's a typo, this should be a plus. We're adding these up. So I'm going to add all these up, then multiply by 1/2, and we should get 8.1431. Now, let's check out how to do this on the calculator, and let's practice. The function that we're using is the square root of 1 plus x squared because we're trying to find the arc length of 1/2 x squared. So I'm going to put that in here in my y equals for my function. Then I'm going to go to stat and edit. I'm going to clear out what I have in there. So I'm going to highlight my L1 and I'm going to hit clear, enter. And I'm going to come over here, I'm going to highlight my L2 and hit clear, enter. So now I can start over from scratch. So I need to put in my midpoints. And I found that my midpoints were 1.25, 1.75, 2.25, 2.75, 3.25, and 3.75. So now that I have my midpoints entered here, I'm going to go back to my home screen and I'm going to tell the calculator to take my function that's in y1 and evaluate it for all of the values in my list 1. And I want to store those values in list 2. So when I go back to stat and edit, I can see all of my corresponding values of the function. So now what I want to do is I want to add all these up and multiply by the width, which is 1/2, the width of my rectangle. So I'm going to go to my list menu that's above stat. I'm going to hit second stat, and I'm going to arrow over to math. And I'm going to tell it to do number 5, which is to sum everything in list 2. Now I have to multiply it by my width of my rectangles. So I'm going to multiply it by 0.5. And so I get 8.14307. Here I rounded to 4 places, but if I round to 4 places, that 7 would make this 0 bump up to a 1, and I would get the same thing here. So this saves, I think, a lot of time and possible mistakes with arithmetic once you get the hang of where all the buttons are located or all the functions are located. So now we're going to review the formula for the area of a trapezoid, because the next method we're going to learn about for numerical integration is called the trapezoid method. And so we're going to break down the areas under the curve with trapezoids rather than rectangles. So here's our trapezoid, just a general trapezoid. The area of a trapezoid is given by this formula here. So we have 1/2 times the sum of the heights on either side of the trapezoid times the width of the trapezoid. So if we imagine that we have some curve here, then we split up our interval into subintervals. So the points here are going to touch the function. So imagine you got some curve here that looks like this. So we're going to find the area of number 1, the area of number 2, the area of number 3, 4, and 5, and so on, and then add them up. So if I find the area of this trapezoid here, I have to take 1/2 and multiply it by the two sides, add it up, times the width. And then I do that for each of these. But what I want you to notice, and why it's important, because this is in the trapezoid rule, this side right here is in common with the first and the second trapezoid. This side right here is in common with the third and the fourth trapezoid, and so on. So the interior heights, when you look at the interval, the interior heights repeat. So this H2 is also down here. This is the right side of the first trapezoid, but the left side of the next one because they touch. So notice how they repeat. So each of these show the individual areas for each of these trapezoids, but if I wanted to estimate the area under the curve by adding up all of these trapezoids, when I add them all up, I'm going to have 1/2 times the change in x, and then I add up all my heights. So I got h plus h2 plus h2 again, which gives me 2h2. Plus h3 gives me 2h3. Plus h4 gives me 2h4, and so on. So the interior heights are going to be doubled, where the endpoint of our interval of interest is not going to be doubled. So this height and this height is not going to be doubled on either end. So that's where this formula comes from for the area approximated using the trapezoidal rule. You're going to take 1/2 times the width of the trapezoid, and then you're going to add up all the heights. But you're going to find the heights by evaluating the function at those points on either side of the trapezoid. And remember that the interior ones overlap. So the first one and the last one is not going to be doubled, but all the ones inside are going to be doubled. So we're going to use the trapezoidal rule to estimate the area under the graph of x squared on the interval from 0 to 1, and we're going to use 4 subintervals. Since our interval that we're looking at is from 0 to 1, to find the width of each of our trapezoids, we're going to take 1 minus 0 and divide by 4. So each width is going to be 1/4, or 0.25. Here's our function that we're trying to find the area under the curve. And so the endpoints of our subintervals are going to be 0, 0.25, 0.5, 0.75, and 1. So when I evaluate these values by plugging them into our function, these interior ones are going to be double because they share a side in common. This right here is going to be counted in the first and the second trapezoid. This height right here is going to be counted in the second and the third. And this one here is going to be counted in the third and the fourth, where these on either end of our entire interval are only going to be counted once. So I'm going to take 1/2 times our delta x, which is 0.25, and I'm going to evaluate the function at 0. I'm going to evaluate the function at 0.25, but I'm going to multiply that one by 2. Same thing with these, and then the last one I'm just going to evaluate at 1. When I work all of that out by hand, I get 11/32. Let me show you how you can do this on the calculator. Let's practice. So I'm going to go put in my function. Our function that we're using is x squared right now, so I'm going to put in x squared. Then I'm going to go to Stat and Edit and put in my endpoints that I want to evaluate. Now, because I want to do this twice, I'm going to put 0.25 in twice. I'm going to put in 0.5 twice. And then I'm going to put in 0.75 twice. And then this one, I'm only going to put in once. All right, so now I'm going to go back to the home screen. I'm going to hit the vars button. I'm going to go over to yvars, choose function, and hit y1. I want to evaluate all of my points in my list 1 using the function I have stored in y1, and I want to store that in my list 2. So now when I go back to stat and edit, you can see all my values of the function are stored here. So now I want to add all those up and multiply by 1/2 and 0.25. So I'm going to go to second stat to access my list menu. I'm going to go over to math and choose sum. I want to add up all the values that are in list 2. Then I want to multiply. So everything we've done so far is just adding up all in here. Now I want to multiply that by 1/2 and 0.25. So we want to take 2.75 and multiply it by 0.25 and 1/2, 0.5. And we get 0.34375. Now, if I check to make sure that's equivalent to what I got when I did it by hand for 1132, for 11 over 32, if I take 11 divided by 32, I can make sure that it works out the same, and it does. So now we're going to talk about absolute and relative error, and we're going to use these methods to compare the actual value of the integral to our approximation using the midpoint or the trapezoidal rule. So to find the absolute error, you're just going to take the actual value and subtract the approximate value. In the rule here, it shows absolute values. However, I personally like seeing the pluses and minuses and doing it without the absolute value, because then that will help us understand if it's an over or underestimate. Okay, so we're going to calculate the absolute and relative error in the estimate that we did for finding the area under the graph of x squared from 0 to 1 when we use the midpoint rule. Okay, so here's the actual value. If we take and integrate x squared from 0 to 1, which this is pretty easy to do, so we can check it, we're going to get 1/3. When we did it using the midpoint rule and we approximated the area, we got 0.3281. So to find the absolute error, we're going to take the actual value minus the approximate value. So I'm going to take 1/3 minus our approximation, and we get that there's an error of 0.0052. Now, because this came out to be positive, I know that the actual value is bigger than the approximate value, which means that our approximation is an underestimate. For the relative error, you're just going to take the absolute error and divide by the actual error and turn that answer into a percentage so that you can see what the error is in terms of a percent. So when I take 0.0052 and I divide it by our actual value, we get 0.0156 approximately. I rounded that. And then when we change that into a percent, this tells us we have about a 1.56% error. Now, using that same method again to find the errors, we're going to do the same thing, but we're going to find the error using the trapezoid rule. So the actual value we said was 1/3 of this integral from 0 to 1. And then when we did it using the trapezoid method to find, we approximated the area under that curve to be approximately 0.34375. So to find the absolute error, I'm going to take the 1/3 minus our approximation, and we're going to get negative 0.01041. This negative tells me that our approximation is larger, which means we had an overestimate. Now, for the relative error, We're going to take our absolute error and divide by the actual error, and we're going to get negative 0.03123. And then we put that in terms of percent. Our error for this is an overestimate by about 3.123%. So you can see in this case that the midpoint rule came out more accurate than the trapezoidal rule. Okay, so in the previous two examples, we were able to compare our approximation of the area under the curve with the actual integral, the actual value, because the integral that they gave us to check was something that was easy to evaluate. Usually, we're not going to have that luxury if we're using these rules. If we're using the midpoint or the trapezoid method, it's probably because the integral is too difficult to try to directly integrate using the methods that we've talked about so far, like trig substitution or integration by parts or U substitution. Those methods are typically out the window if we resort to using the midpoint and the trapezoid rule. So we typically don't have the actual answer to compare. So that brings us to this theorem, the theorem for the error bounds for the midpoint and the trapezoid rules. Often helpful to find the upper bound for the error when you're using some approximation method. And so this theorem provides us with that. It helps us determine how many subintervals to use to come up with like a bound for your error. So this here is the formula if you're using the midpoint rule, and here is the formula for the trapezoid rule. So you'll see that this is labeled M for midpoint and this is labeled T for a trapezoid. Okay, now let's see how this theorem works. Question is asking for what value of n should be used to guarantee that an estimate of this area under the curve e to the x squared from 0 to 1 is accurate within 0.01 when we're using the midpoint rule. So it's asking for the number of subintervals that we need to break it down into in order to come up with an answer that is within 0.01 of the actual answer. The first thing we need to do is come up with our value of m from this formula. And it's asking us to do this if we're going to perform the midpoint formula. We're going to use this formula right here, this first one with the mn. This m right here represents the maximum value of the absolute value of the second derivative over our interval of interest. So we need to find the second derivative and graph the absolute value of the second derivative over the interval that we're interested in and look to see where the highest point is on that interval. To find m, we have to find the second derivative. So here's the first derivative. I take e to the x squared, and then because I have this inner function, x squared, using the chain rule, I have to multiply by the derivative of the x squared, which I get 2x. Now, when we take the second derivative, I'm going to have to use the product rule. So when I take the derivative of this, I'm going to use this as my first function. I'm going to take the derivative of e to the x squared, which we know is e to the x squared times 2x, and I have to multiply it by this function here, 2x. So I have e to the x squared times 2x times 2x. Now I have to add the derivative of the second function times the first. The derivative of 2x is 2, and then I have to multiply it by e to the x squared. And when I combine this 2x with this 2x, I get 4x squared e to the x squared plus 2e to the x squared. So on my calculator, I'm going to graph the absolute value of the second derivative. And then I'm going to look at it on the interval from 0 to 1 and look to see where my highest point is. If you graph that on your calculator, you're going to find that your highest point is at x equals 1. So to find the maximum, I'm going to plug 1 in for x. So I plug in a 1 here, a 1 here, and a 1 here. And when I clean it up and I evaluate it, I'm going to get 6e. So 6e is our m. So that's our m for our formula. Now the a and the b is the upper and lower limits for our interval that we're integrating over. So that's a is going to be 0, b is going to be 1. Now, when I use that formula for the midpoint, I'm going to get 6e, and then I'm going to multiply it by 1 minus 0, that's my b minus a, all over 24n squared. And I want this to be less than or equal to 0.01 because I want it to be within an error of 0.01. So when I go ahead and solve this inequality for n, I get that n has to be greater than or equal to the square root of 6e over 0.24. And when I evaluate that, I get 8.24. And since this needs to be a whole number because we're trying to find the number of subintervals to break up the interval from 0 to 1, you're going to always round up to the nearest whole number. So in this case, it would be 9. So if I use 9 subintervals using the midpoint rule, when I approximate this integral, or the area under the graph of e to the x squared on the interval from 0 to 1, I should have an error that would be less than or equal to 0.01. Okay, here's the last method that we're going to use in this section. This is another way to approximate using numerical integration. This is called Simpson's rule. So the first rule we went over was the midpoint rule, and that's basically the idea of using constant piecewise function. Then when we move to the trapezoid method, what we're looking at here is a piecewise function using linear functions of a form like mx plus b. So now Simpson's rule, what you want to think of Simpson's rule is, you're thinking about it in terms of making a piecewise function with a quadratic. So we're going to have curved top pieces. So that's what we're looking at. And so here is our rule for Simpson's rule for approximation. We're going to find the width of our interval, divide it by 3, and then we're going to multiply it by all this stuff inside the parentheses. I want you to notice the first value and the value have a coefficient of 1. The inside values, those inner values, alternate from 4 to 2. So this is 4, this is 2, 4, 2, and then it keeps going and repeats the pattern, and then the last evaluation here has a coefficient of 1. So there's what we're going to be doing here in order to use Simpson's rule to approximate an area under a curve. And if you want to find your error bound for Simpson's rule, here is your formula for that. All right, so let's look at this example. It says use S2, meaning Simpson's rule with 2 subintervals to approximate the area under the curve of x to the third from 0 to 1. And then we're going to estimate an error bound for S2. So we have 2 parts to this. First, we need to approximate the area under the curve. So using Simpson's rule, we're going to find the width first of each of the subintervals. Since our upper and lower limits is 0 to 1, I'm going to take 1 minus 0 and split it into 2 subintervals, which gives me a width, or a delta x, of 0.5, which means my endpoints are going to be 0, 0.5, and 1. So my first interval is going to be from 0 to 0.5, and then my second subinterval is going to be from 0.5 to 1. Now, according to Simpson's rule, I need to take my delta x and divide by 3. And then on the inside, when we evaluate our function, the endpoint of our limits, the 0 to 1, right? Not the subintervals, but the interval from 0 to 1. This has a coefficient of 1, and this has a coefficient 1. And then on the inside, it alternates between 4 and 2, starting with 4. So this is going to be evaluated at 4 times f of 0.5. So when you add all this up and multiply by 0.5 over 3, you're going to get 1/4. Now, if you use the trick in the calculator with the list and the function, you want to put your x to the third and your y equals for your function. And then for your endpoints, you're going to put in 0, 0.5, and 1. But because this is done 4 times, you're going to put in 4 0.5s. So in your list, you'll have 0, 0.5, 0.5, 0.5, 0.5, and 1. Okay, so this is our approximation using Simpson's rule. Now, if we want to find the error bound, we're going to use the formula that's above. Now, in our previous example, we used that formula to actually find how many subintervals if we want a certain error. And the example that we're going to work now, we're doing it different. We're doing it in reverse, where we know what our subintervals are, what our n is. Our n is 2, and we want to find how much error that would give us. What's our cushion? What's our give and take? What m represents for Simpson's rule for the error bound formula is going to be different from the midpoint. So notice in here, m is defined as the maximum value when you take the fourth derivative of the function and find the absolute value and graph it over the interval from a to b and find the maximum value on that interval from a to b. So for this one, we actually have to find our fourth derivative to find our value for m. So our first derivative of x to the third is 3x squared. Our second derivative, now when I take the derivative of 6x to get the third derivative, that gives me 6. And then to find the fourth derivative, when I take the derivative of a constant, I get 0. So in this case, m is going to be 0. My a is 0. My b is 1. That's my interval for my upper and my lower limits. And then I know my n is going to be 2 because we want to do this in 2 subintervals. So if I plug that information in here, I get m is 0, the difference between a and b is 1, and then according to the formula, I put 180 down here, and I do n to the fourth here, which gives me 16. Now, this doesn't even really matter, because if you see m is 0, then our answer is going to be 0. We're going to have no error. If this is saying we get no error, then our approximation is going to be what the actual value is. And when we go through and check that, if I integrate from 0 to 1 for x to the third, I'm going to get x to the fourth over 4. And when I evaluate it over the interval 0 to 1, I get 1/4. So the exact value matches our approximation, and that's why we got a 0 here for no error. Okay, here's our last example of the section. We're going to use Simpson's rule, but we're going to use it to find the arc length of the curve y equals 1/2 x squared over the interval from 1 to 4. And it's telling us to use Simpson's rule and to use it with 6 subintervals. So to find our delta x, our width, we're going to take 4 minus 1 and divide it by 6, and we're going to get 1/2. So our delta x, or the width of our subintervals, is going to be 1/2. Now, because we're trying to find the length of the curve rather than the area under the curve, we need to use the arc length formula for our function. And if you recall, the arc length formula is the square root of 1 plus the derivative of the function squared. In this case, if I take the derivative of 1/2 x squared, it just gives me x. And then when I square it to plug it in here, that gives me x squared. So the function I'm going to use is the square root of 1 plus x squared. So if I do this using the calculator, this is what I want to plug in for y equals. Now the endpoint, since we're going from 1 to 4, we're going to start at 1 and we're going to keep adding a half until we get to 4. So I'm going to go from 1 to 1.5 to 2 to 2.5, etc., all the way up to 4. So here are endpoints. Now, using Simpson's rule, I need to take my delta x, which we got was 1/2, over 3. When I evaluate my function at the endpoints, the first and the last are going to have a coefficient of 1. So that's 1 times f of 1 and 1 times f of 4. That's my first and my last endpoint. Then inside, it's going to alternate, starting with 4, My coefficients are going to alternate from 4 to 2, 4 to 2. So 4, 2, 4, 2, 4. Now, when you put that all in and whether you do it by hand or using the calculator, you should get 8.14594. If you use a calculator, don't forget, since you're doing 4 evaluations at 1.5, you need to put in 1.5 4 times in your list. For 2, you would put it in 2 times. Then you would put this in 4 times, this in 2 times, this in 4 times. And then 1 and 4 would only go in 1 time. So, to wrap it up, we covered numerical integration. We covered how we did 3 different methods you can use to estimate the area under the graph, and we resort to these methods when the typical or traditional methods are too difficult. And so we talked about the midpoint rule, the trapezoid rule, and Simpson's rule. We also talked about the error and how we could calculate that. And lastly, I showed you how to use your calculator to save you some work with this arithmetic, which I highly recommend.